Hey everyone, a very happy Tuesday and welcome back to our ARM Tech Talk series. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. It's so great you could join us, whether it's your morning, whether it's your evening, wherever you're joining us from. Welcome. It's great to have you. Today we've got a really exciting ARM Tech Talk lined up from Siemens. We're going to be following on from some really exciting announcements you may have seen a couple of weeks ago, focused on our automotive side of things. And we had some really exciting announcements where we brought some fantastic innovation from ARM to the world. We brought, for the first time, ARM v9 based technologies to automotive. And particularly what we're going to focus on here is something that was really brand new for us in the industry as part of this announcement was the virtual prototyping that we announced. You know, this latest generation ARM AEIP and virtual prototyping on this IP, allowing software developers to start before the physical silicon's even available. And we are super excited today to have Siemens, one of the partners we partnered with as an industry leader, to deliver these virtual platforms to accelerate your time to market. So I've got a couple of just intro slides to go through. If you've attended one of these talks before, you know the drill. And then we're going to get right to the meat of this really exciting tech talk from Siemens with some fantastic demos and I'm sure a ton of great questions from you guys as well. So Lee, if it's all right with you, can we head to the next slide, please? If you want to get involved in the conversation today, in addition to asking questions in the Q&A box in the event page, which you should be able to see, so please do that. If you're joining on YouTube, just head to the link in the description to access the Q&A. You can access all of our prior tech talks on demand at youtube.com/arm, and you can access all of our upcoming tech talks at arm.com/tech talks. So do make sure you register for those. We're carrying on the theme of virtual prototyping in next week, actually. We're going to be hearing from Corellium, another partner who featured as part of our automotive launch. So make sure you register for that if you're interested in this topic and you want to hear more about how you can really accelerate that time to market in automotive and how ARM and our partners enable that, then do join our webinar then. So let's head to the next slide where we get a fantastic little bio and photo of our presenter today. And I'm actually going to bring him straight onto the stage as well. I'm delighted today to be joined by Lee Gu, who's one of the as an account technical manager at Siemens and who's going to be giving today's ARM Tech Talk. So before I hand over to you, Lee, just a final reminder, if you've got any questions, pop them in the Q&A box. We'll get to those at the end. Lee, thank you so much for joining us for today's ARM Tech Talk. I know it's super late where you are as well, so I really appreciate you staying up and making the time to talk to us today. It's over to you. Please take it away and talk us through what you guys have been working on at Siemens.
Yeah, thanks, Tobias. It's my pleasure, really. So, hi, everyone. I'm Lee. As Tobias said, I'm an account technical manager from Pave 360 team of Siemens EDA. My talk is about how do we make it possible for automotive products early testing and validation using our digital twin solutions. So needless to say, creating a vehicle is a challenging task. Traditionally, a car has long, expensive development cycles, integration nightmares, using black box SoCs and ECUs from suppliers and lack of sufficient full system for testing capabilities. Nowadays, a car needs to be intelligent and should be equipped with much more features. Consumers want new features fast, but automotive tech is complex and cannot move fast enough. The introduction of new technologies and methodologies, including ADAS, high-level ADAS, autonomy, and software-defined vehicles, SDVs, are making this even harder. Therefore, automotive supply chain now faces major transformations. Previous methodologies are no longer sufficient and often impede accelerated innovation, makes it difficult for increasing vehicle complexity support. One of the significant industry trends in automotive is the desire to shift hardware and software development left. But what does that mean? As shown in the diagram on the right, at present, a significant portion of the software development effort follows hardware development, which can often lead to delays. The hardware development process itself often involves several expensive iterations of hardware prototyping. So we need to shift left and use digital twins. This means hardware and software can be developed in parallel, speeding up this process. Furthermore, many early iterations of the hardware could be tested in virtual prototypes for substantial cost savings. A fully functioning digital twin should be able to address all challenges for next generation automotive design. First of all, the integration storm. Technology vendors often don't expose the details of what's under the hood for their tech. This makes integration of technology immensely difficult and adds to the integration time. Digital twins at varying fidelities offer a lot of metric that can be used to understand the behavior of supplier components and make integration easier and predictable. Because with a CI/CD in place, we expose issues as early as possible. That's the nature of it. Secondly, the lack of full system view, combination of high complexity, new features, and closed boxes from vendors make it almost impossible for OEMs to truly understand system performance. How can you make sure your product is going to perform as expected if you can't truly measure its performance? The metrics a digital twin provides can help to understand performance and allow for exploration of solutions at a very early stage. These capabilities make shift left happen for all players in the automotive supply chain. So as of now, OEMs, Tier 1s, Tier 2s, and IP providers use PAVE 360 Digital Twin. OEMs specifically use it to explore new architecture possibilities and validate real-world use case. Tier 1s use it to provide proof of value to OEMs by integrating new functionality and demonstrating the value of that functionality in real-world scenarios again. Tier 2s use it to understand complex compute requirements and inform decisions on the next generation SoC architectures. So IP providers, last but not least, use it to enable their customers to evaluate IP configurations for optimal results and validate real-world use cases way before silicon can be made available. So wherever you are in the supply chain, we're there to help. So before we talk about the technical details, I would like to mention our collaborations. So we have been working with industry giants, ARM and AWS, to bring fundamental change to the automotive ecosystem. By working together with ARM and AWS, Siemens PAVE 360 enables access to ARM-based systems as holistic digital twin solutions. Solution can be hosted in the cloud, making pre-silicon system design a reality with a fast and low barrier to entry. As a matter of fact, ARM's latest IP announcement emphasizes the value of virtual platform, a focus on virtual environments that speed up and shift left SDV development. This again re-emphasizes our digital twin approach for early software and hardware development before silicon is made. So how can we build a digital twin platform to start addressing automotive use cases today? This is a bird's eye view of PAVE 360 digital twin solution. The system is an end-to-end digital twin platform comprising a digital twin backend that executes modeled hardware and software, application software, and it also consists of a front-end IDE used by software and systems engineers to explore, measure, analyze total system designs. The backend allows for exploration of underlying hardware architectures using PAVE 360 Virtual, which models the system hardware as virtual models in System C or TLM, and allows user to run different workloads. Ultimately, this helps you to understand the system architecture, like how many cores, what hardware accelerators are needed, what bus interconnect configurations. The backend also allows you to exercise your software by utilizing real-world and synthetic stimuli using sensors, actuators, and external hardware. Essentially, this allows your total system simulation to run very fast, so you can quickly evaluate design decisions and trade-offs. We enable the efficiency by using accelerated pre-silicon software development environment. I'll show you some real-time ADAS demos running on example system designs. The hybrid, which is very important as well, it is in the backend, allows for high-fidelity simulation when you want an accurate measurements for specs like latency, bandwidth, critical path timing, power consumption, etc. Those are more related to hardware metrics. It operates in a run accurate mode, so you can get the most information possible to characterize your system. Also, systems can run as a mixture of run fast and run accurate, where you can configure both to help optimize the simulation time. I'll show you a use case eminently. So for the context, we already covered Pave 360 front-end IDE in our last tech talk. Feel free to refer to it on YouTube. Today, I'll just quickly show you what it looks like. So the front-end IDE is an Eclipse-based interface where you can configure your software, payload, and hardware design. For hardware, you can configure CPU clusters. This includes ARM IPs like A53, A72, and the latest ARM Hunter IP support being added to. So you can add ARM NPUs for AI inferencing. For software, you can add different types of algorithms like periodical events, like sensor input. You have like images or whatever you name it, IMUs coming at a fixed interval, and the custom payload like SIM understandings and object detections. The IDE will show you indicative metrics such as latency, CPU utilization, etc. It is a typical iterative feedback design workflow where the software takes an input of the software and hardware co-design and runs simulation to give you metrics for analysis. We then check if if your specs are met. If not, you just repeat the process until you are happy. Here's a case study to find the best architecture for AI inferencing using ARM IPs. We take A55 core as the choice of CPU, considering power consumption and efficiency, and etc. And Ethos N78, which is an accelerator IP from ARM as an NPU. So you want to know for the three following configurations, which is the best in terms of a speed. So first of all, use just single one A55 for AI compute. And secondly, use two A55 cores for AI compute, like using parallelization for speed up. And lastly, use an N78 NPU for AI compute. The answer could be obvious to many of you, but we need to quantify it like in a scientific way. So the idea is to design a system with a mixed fidelity setup. So run fast in virtual platform, where both Cortex A55s are configured, and then the N78 RTL is configured in a Questa simulation, which is another emulation and simulation product from us. So the results looks like this. We perform the same number of AI inferencing for all configurations. The baseline, the example AI workload hammered core 1, where it says 100% utilization during the inferencing, and it runs the slowest. For the CPU accelerated version, the second version, where both CPUs were used for AI inferencing, though it runs faster, but both CPUs says 100% utilized during inferencing. Not helpful. Lastly, we offloaded AI inferencing onto the NPU. CPU utilization drops dramatically, and the simulation finishes much faster. So after all of this, we quantified the benefits of using NPU plus CPU design for the task using mixed fidelity. So then we have confidence to move to the next stage. So we have hardware designs with software validated on top. And this design can do AI inferencing, pretty good. We might also have other hardware components, such as control ECUs, sensor ECUs, digital cockpit. How do we test a complete, a typical ADAS tech stack with everything integrated, like you will normally do every day for automotive development? And also how to do that in real time. A typical advanced driver assistance systems, ADAS tech stack, involves multiple hardware components working together. We need to have full metrics with all systems integrated. We can commence the integration and testing on day one with the help with the backplane. We call it Pave 360 backplane. It builds an open environment digital twin solution. It manages multiple sources, both Siemens and third parties, selected SoCs with different IPs such as ARMv8, latest v9 IPs, ECUs, you name it. We also provide accelerated pre-silicon software development simulation environment, so the simulation can run real time. We boost the simulation speed to 50 to 70 times compared to conventional methods. So with this, we can build complex mixed fidelity digital twin quickly and in the cloud. Here are the key steps to build a full digital twin system for early testing Obviously, the first step will be to build a digital twin system of subsystems. Subsystems, by that I mean ECUs and all the components I mentioned. Then we enable routing between each system by creating gateways for each of them to handle ingress and egress of data through the backplane. Finally, we simulate the system in a synchronized manner. With that, we have a closed-loop testing environment for end-to-end testing. The simulation backplane can facilitate FMI, FMU interface connections, TLM connections, bridge protocol models such as CAN, IP, Ethernet, and others. It supports a wide range of clients, simulation models, MATLAB, Simulink models, or any other virtual platforms. We create a boilerplate code for you so you can build a digital twin in no time. You can build it programmatically or use the digital twin description language, which further shortens the development time. By that I mean in a matter of hours. The backplane has cross-platform support, obviously. You can have your simulation engine running in Windows, providing synthetic data, while central compute running on a Linux embedded platform. The communication between the server and clients is established using the TLM API ROSI client portal, which is used to establish TLM 2.0 channels. The development effort would be to create appropriate gateways, and the backplane will synchronize across platforms. As of today, we have 15 gateways exist, which can connect majority of the digital twins you can design. So through the digital twin, all you can do, we have unified timing where you can easily debug all corner cases with the ability to pause, replay across clients. So for example, for typical robotic or automotive development, you use ROS, right? So we take ROS gateway as an example. If you are using ROS for development for automotive functionalities, the ROS gateway will act as a clock server by synchronizing the backplane simulation time with the ROS simulation time every RTOS interval. So without further ado, I think, let's see some digital twins in action. So here's the design. First of all, it is a deep learning-based full ADAS stack. The system includes virtual sensors from Kala, which is an open source simulator designed to support development, training, and the validation of autonomous driving systems. So it also has a centralized compute with deep learning-based autonomous driving model, and finally a digital cockpit view, all running with ROS gateway plugged into the backplane. Note that the central compute with AI inferencing runs with accelerated software dev environment with GPU pass-throughs on an AVA reference platform, which is also one of the reference platforms from ARM. The platform is equipped with Neoverse N1 CPU and an NVIDIA RTX A2000 GPU. The end-to-end testing is very easy to start. We provide necessary scripts to engage the containers or environments. We recommend container-based approach because it's easier for CI/CD. We typically start the backplane server like I just showed in a video. The server will wait for all the clients to connect, and the clock starts ticking, so moving the simulation forward. You can see the car start driving. That means everything functions well because the model perceives sensors from the simulation and make the decision for driving. So the DL model we used here is a customized implementation of one of the latest research work for complex urban driving. It consumes one front camera with wide angle, one GPS, and an IMU. The model generates throttle, brake, steering signals for control, and a rich list of other perception results for the environment. For example, the bird's eye view map with segmentations, probabilistic depth map, a lower half in the infotainment system, a digital cockpit, as you can see. And in a typical ADAS stack, you need those information for redundancy in terms of safety, and you could also use those information for infotainment, also for debugging. For example, a car stops before a junction, and it could be that the traffic light is red where you're about to see, or there's a pedestrian crossing the road, or even there's a car cutting in front of you, all of which help you understand how black box-like autonomous driving system make decisions. So as you can see, you can observe in the bird's eye view map that like traffic light signal changes, and that's why the car stops. But I mean, we can talk a lot about AI systems, and we can go deep into these topics for another day. But the idea is that DL inference runtime SDK decouples the hardware acceleration. It means that you don't need to change a single line of code as long as the AI compute a runtime delegate. There's a delegate for your target hardware. So with the software running the virtualization and accelerated environment, you can test everything, and later you can just plug in the real hardware, and it will just works without too much surprise. So the system will keep going. So we'll pause from there. Move next. So the model drives perfectly in the last demo, but you might not be able to do that all the time. Let me show you how we can debug a sophisticated multi-platform system with our digital twin. So this is a case study here where autonomous driving stack freezes for some reason. And the demo is recorded by one of our great application engineers. Here we'll be using VS Code and its Python debugger to attach to our running processes. The simulation has already been kicked off as we speak. And let's go to the part where the system will just hand. This is a different map with the earlier version of ADAS tech stack. It's different from a deep learning based model. And the car is going to drive to a point. I think it's here. Yeah. It will freeze. So here, the system is hanging. It did not crash. So there's probably a deadlock somewhere. Now let's try to figure out how to debug this. So if we switch back over to our Visual Studio, as we do here, we set up all the configurations as we can see. Go to the debug mode. So there's a debug switch over here. This drop down of different kind of configurations that we can attach, created over there. Let's say we want to attach to the PAVE 360 ROS gateway process. We find that process ID. There we go. So now we have attached to it. What we can do now is actually go to source code. So we go down to the PAVE 360 ROS gateway. We go to the source. We know the system gets stuck, right? So what we have done is that we put breakpoints in the places we think that might cause the issue, just to see where the system is actually sitting at. So we know it's not happening. No, it's not happening there. Nothing is hit because then we put a breakpoint somewhere else, like in here. That's suspicious. But again, nothing is hit again. So what about normally 99% of the time it's a loop. So yeah, here we go. We have a hit. So what happened here is that we know the system gets stuck here. We know that, I know that before this, like one of the publishers that we subscribe to has died. So if we go back over to one of the nodes and to the command line, so that can be helpful too. One of the debug messages says that it gets printed out and there's not enough of waypoints. So no more waypoints. So basically from this point here, we are going to for normal debugging process where you go to go from where something's going wrong and click into different kind of functions. Here we are at this finding trajectory function. We know it is not returning correctly. For example, if it's not, non-true or whatever, the path points is empty. So we kind of peel the onion, go back to this function to find out where the issue is. We've basically narrowed it down to the publisher numbers check. So what we do is that if the publisher number is not 0, then we basically record the number and check the number again in the loop. By the way, this is no recommendation or best practice in actual coding. It's just quick debugging. It only serves as an example of quick debugging demonstration purpose. Anyway, so after that is done, we record the states of the publishers and checking if that's non-zero. Only if that's non-zero, we enter the loop. Otherwise, we get out of the loop. In this case, the system should not be hanging anymore. So let's make sure it's compiled. And we will start the backplane again, start the ROS nodes that will bring up all the portals. Okay, so let's do that. So this time, as you can see, we have done a couple of things in the code and we compiled everything. The system shouldn't be going into that loop or stuck into that loop, which means the vehicle should proceed without hanging at the end of the trajectory. There we go. We expect it to exit successfully. Cool. So what we have done here is we have a full tech stack ADAS solution, one of the example running on a virtualized platform. With everything integrated together, you have a full testing capability of a complex system, and you can debug across it and find the issue and solve it in no time, like normal software development. So now I've shown you how to test everything in simulation. On a local machine, remember that's an AVA machine. What if you don't plan to own an expensive piece of hardware on day one? And what happens when you have real hardware manufacturer to test? So the next demo shows you that we can interconnect with physical devices seamlessly once you have them in the cloud. So this is a system we deployed to AWS for early access. One can spin off Pay360 EC2 instances easily. This is a 6-client demo, a bit more complex than before. It also has a slightly different ADAS tech stack. There isn't an centralized AI model in the sense that it controls, it does the perception and also controls the vehicle. Instead, we have this classic planning, perception, control ADAS stack. Normally, you would have like a localization layer too, but here, let's for simplicity, we just use the ground truth GPS from Carla. So what is also new here is a 1/10 model car called MARV. We call it MARV, meaning Mini Autonomous Reference Vehicle. It is an RC car equipped with camera, JSON board for the control. What you will do, it will receive control signals that's replicated, which was originally sent to the virtual car in a Carla environment. You can see that both of them are controlling perfectly. So we have the following clients here to dig down deeper. Planning model as client 1, Carla sensors as client 2, perception model as client 3, AI compute as client 4, digital cockpit as client 5, and an RC car, obviously, to mimic Carla vehicle controls. Imagine it as your testing hardware as client 6. So client 4 is interesting. It has the accelerated environment, which enable us to simulate in real time. So you can see everything working together in live. And it runs on AWS Arm Graviton too. This client can be deployed to platforms with NPUs, GPUs, or just CPUs, depending on your choice of target platforms. All the other clients runs on an AMD EPYC EC2. So demo shows that the verified algorithm and tuned control system can be seamlessly deployed to a reference hardware with just minor effort. By that I mean, for the process to happen, you first need to log into the EC2 instance with our Pay360 environment. We use the same script to kick off the simulation. You can see all clients all up and running. Note that MARV car is also connected via this script, kicked off by this script. It's running on a local desk. You can see that control signal is synced with the virtual car. This is done by duplicating, like I said, from the control signals from the planning module in client 1. You can imagine it as you need to tune a different version of production PID controller because the simulation might behave a little bit differently. That's the extra little bit of effort I need to mention. you can have hardware in a loop testing as part of the CI/CD process. Once you have the hardware to tune the IDE, on the one side, you test all the software in the virtualization, making sure on the algorithm level, everything works. And on the control level, you have hardware testing in the loop. So with the solution in the cloud, the R&D team can really fully embrace the SDV. Every time development team makes a change, the CI/CD will pick up the new commit from staging branch and launch the regression process to test as many scenarios as you define in the cloud. You'll find that metrics an outcome after launch break or overnight if it runs longer. This can happen with your own hardware design before you have your hardware. So I believe this concludes my presentation today. Thank you all for joining. I'm happy to take any questions.
Let's do questions. Thank you so much, Lee. That was a lot of amazing technical content and some really, really great demos. So thank you for pulling that together, and thank you to the whole team for putting it together. And it's, as I said at the start, it's great to have Siemens being one of our partners for the launch we had a couple of weeks ago, where we launched our new automotive enhanced IP, and this virtual prototyping aspect of the launch is absolutely key for developers out there as well, and it's super critical for the whole automotive industry. So thanks for all your great work in this and for a great presentation. And this won't be and as you said, we heard from you in September with some great presentation there, so do go and check that out on YouTube. And we're going to be hearing from you in a couple of weeks' time, which I'll come on to in a bit. And now it's time for questions. So if you've got any questions, please use the Q&A box on the event page. We've definitely got a few minutes for those, so ask away. And I've got a couple of questions I'd love to ask Lee as well, and I'm sure you do too. So do get them in, and we'll get to those in a moment. So you talked about, right at the start, you talked about shift left, right? And for those who maybe joined a couple minutes late, or for those who kind of are looking for a summary here, how would you summarize how you feel customers are going to gain an advantage with this significant change in the automotive development industry, for software development, this shift left approach? What do you feel customers are going to gain most from this?
Yeah, so shift left, thanks for that, Tobias. Shift left is essential for SDV development next generation. So without it, developers face difficulties in integration and system level testing. Consider that the traditional routes developers take require the hardware is available before software development can begin. This inherently limits the function and features of software that can be developed due to the limitations of what's often older technology. So for example, if ARM releases a new CPU, it takes 2 years before even gets to the silicon. Once in the silicon software development, the team can begin, which can take a minimum of a year. Just throw that number out, might be longer even. So integration into the vehicle platform can take another 2 years. So at that stage, when the customer receives it, the technology is already 5 years old. So the customers really want that tech in their like they want the tech in their phone, like in their cars, but not tech that's 5 years old. So shifting left means that starting with software and optimizing hardware to meet those demands. The only way you can effectively go software first is to develop on digital twins way before any silicon is available. So, and secondly, you can leverage system level and real world stimulus with the digital twin solution. Developers can ease the integration problem because functionality can be tested in the environment, in system, giving a greater level of confidence that the entire system will come into a piece and when the silicon eventually arrives. So I think that's the last point. So OEMs and tier ones can become valuable feeders to next generation SoCs by sharing results from software-driven digital twin simulations with their suppliers to ensure that SoCs in design can actually handle the workloads being developed. So really, I think this is the only way that developers can take the next step in SDV development, and we deliver that.
That's awesome. No, thank you for that. And you mentioned, of course, that you mentioned ARM a lot during the presentation, whether it's in the Graviton instances that you utilize, whether it's the Ava development platform, which is which we also talk about a lot of part of Sophie, and also, of course, as we mentioned at the start of the talk, right, the new AEIP, the new Automotive Enhanced IP. I'd love for you to talk a bit more about why is it that you support ARM? Why do you work with ARM so much, and does your digital twin support this latest IP? And could you talk a bit more about that, and how are the ARM's customers going to benefit from that?
Yeah, sure. Thanks for that. Obviously has a large pool of IPs, like it's famous for low latency and computation efficiency, which fits perfectly into the automotive world. For example, you guys have low power CPUs and GPUs and NPUs, like I showed in the presentation. We already support most of them. I'm happy to say that. So to support the latest AE and Hunter AE 720 is a no-brainer. So it will be another powerful extension to the automotive customers' toolbox. So I guess even for also for ARM's customers, it can benefit from this by gaining access to the latest software running on the latest tech right from the launch day. So as early as possible.
It's a massive benefit for the whole ecosystem, and thank you for supporting and thank you for the answer. Thank you for supporting our latest IP A720AE in particular. And we'll talk a bit more about what you're going to be doing going forward in a bit. But we've had a question come in about the technology you use. What technology do you use to actually program the twins, the digital twins? Is it C++? Is it something else? Could you talk a bit more about that? Are you able to share any more details on that?
I will share what I can share. So basically it depends, right? If you're talking about a software level kind of ADAS stack, it's up to you, because to integrate and test everything on a software level, it's up to you to integrate in your own programming language. The demo we showed is a mixed implementation using languages like Python and C++. For early prototyping, if you don't care too much about the efficiency, you can use Python to do all the model and training and inferencing, all of that. But actually, when you want to integrate into the backplane, because like I mentioned, we use ROSI for those intercommunicate, which is really automotive oriented kind of standard. So that guarantees like everything is synchronized. Whatever you tested can be shipped out to the silicon as it is, like with minor corrections or updates with the real hardware. So really on a software level, that's that. Whatever language.
Brilliant. Thank you for that. So yeah, I hope that answers your question, and do keep them coming. We've still got plenty of time for questions. I'd love you to talk a bit more about, of course, you can't talk about our recent Automotive Enhanced IP announcement, the automotive announcement we made, or indeed ARM, or indeed automotive. We're talking about an ARM in automotive we're talking about without talking about AI, right? It's a huge topic. I'd love for you to talk a bit more about this. ARM has a great story with AI. You guys do too. Could you talk a bit more about what you see the impact of these AI applications is for hardware design, and how that ARM and PAVE 360 integration provides a really great solution for customers and developers out there?
Yeah, sure. Thanks for that again. So AI algorithms in its nature are complex and really rely on hardware to accelerate for timing reasons and power consumption requirements. At the same time, AI algorithms tend to evolve very often. So therefore, generic AI compute hardware that can support AI model update frequently is very crucial. Like all the other automotive software development as well. So we also need to test the design on day one, just to shift to left, right? So ARM's accelerated IPs provide very good support for popular neural network architecture, for example, MobileNet or ResNet. That's also what we used for the demos, driving models. Our customers already used PAVE 360 to validate total system designs and make use of the accurate metrics to help them to make the system design decisions. So having the AI purposed IPs from ARM is really a strong extension to the automotive customers' toolbox. to make their design decisions early happen. So I see this a very valuable partnership, really.
Absolutely. No, and it's great you talked about that. And, AI can on ARM can run literally on everything from the CPU to the GPU, accelerators and beyond. So it's great to see that partnership continue and provide some great solutions for the customer. We've had a question come in about what is the maximum number of clients that your backplane could support?
Very, very good question. Thanks. So technically unlimited. So we have I'll go into the details. So we have case studies. We have clients coming to ask us asking about the same question. So what we do is we have provided them with an A client design, so which still runs in real time for an ADAS stack. So they can test that early. The backplane itself is highly optimized and can run hyper real time. But since we run everything in a synchronized manner, so unavoidably, if we keep adding clients, the system will slow down as with any other system in the world. So at the end of the day, it's really a design decision to make with a limited resource. The bottleneck doesn't come from the communication channel. It could be anywhere, right? It could be your digital tool design for compute, one of the components where you connect to the backplane. So we're there to help you to find out the bottlenecks so that you can focus on that unit or scale it to 2 units. So all those are design decisions. So we're here to provide the realistic metrics to make the best design decisions.
Amazing. Thank you for that. We'll mark that one as answered. Thank you. That was a really, really great comprehensive answer. I'd love to talk a bit more about what's coming up in the next couple of weeks. As I mentioned, we've got another virtual prototyping talk next week from Corellium. So do tune in for that one and get yourself registered for that as well. That's super exciting. But I'm also excited to reveal that we will be doing a live stream series of ARM Tech Talks from Embedded World. And we thought, who better to show us some of the great demos at the show than Siemens. So we'll be hearing from you guys again in a couple of weeks. Could you give us a little, I'm sure you can't share everything, and obviously we want to get people to tune in and see what's going to happen live at the show and the great demos you're showing off. But could you give us a little sneak peek at what people could expect from attending Embedded World and going to your booth that runs on ARM, and also if they can't attend Embedded World, what they could expect from joining the ARM Tech Talk and what you're showing off at the Siemens booth? Could you give us a little sneak peek at what's in store?
Yeah, sure. I try my best. So obviously there will be tons of demos, similar but different. We demonstrate we can test and simulate in a simulation environment, virtualization environment, very efficiently, and you can expect to be an open platform where lots of other solutions or different designs can be plugged into it, making it more extendable. So I guess you can look out for that.
Absolutely, and they all run on ARM, which is great. We'll be showing off those ARM-based demos
running
at
on
the show.
Running on ARM with accelerated environment for ARM IPs. Yeah, for sure.
That's super exciting. Super exciting. So do get registered for that. We'll be very shortly releasing the links for that, so you can set a little reminder in your calendar, go onto YouTube and click the live stream, get set a reminder for when that does go live. It'll be a really great 15-minute short little snippet to say, hey, look, this is what Siemens are showing off at the show. So we can't wait for that. Super excited for that. So final question, because we're almost out of time. What if let's say I'm a developer, a customer of and looking and think they've attended today's ARM Tech Talk, they think, wow, this is awesome. I've heard all about Bay 360, some really great demos, really engaging content. I understand how I can use this to really accelerate my automotive development lifecycle. How can they get started on Pay 360 on ARM today? How could they get started? What's the best way for them to go ahead and get started with Pay 360 on ARM today?
Cool, thanks. Very important question. So this platform is actively used now by multiple customers. So I would suggest visit our website and make an inquiry to speak to one of our super advisors. We can offer guidance step by step on how and what to access very easily.
Absolutely. No, so do get in touch. It'll be really exciting to to see what comes of this. I'm sure lots of people will be getting in touch with you guys, and I'm sure lots of people will be attending Embedded World as well. So as I mentioned, do make sure that about wraps up today's Arm Tech Talk, but do tune in next week at the same time, 4 p.m. UK. Actually, no, it'll be 4 p.m. UK, but 8 a.m. Pacific because of the way the time difference works. So not 9 a.m. Pacific. So do tune in then. And we look forward to seeing them for another Arm Tech Talk, this time from Corellium, talking about their work in the automotive space, supporting our automotive launch and virtual prototyping there. As I say, we had we've had some great talks from Siemens, and we'll be hearing from them again in a couple of weeks' time, live from Embedded World. So do keep an eye on arm.com/tech talks. Make sure you're subscribed to our newsletters, so you make sure you don't miss any of our announcements, any of what's coming up, because we've got some very exciting Arm Tech Talks over the next couple of weeks. And as I say, we'll be bringing Embedded World to you, and we'll bring you some great Arm-based demos from Siemens at the show. So do make sure you tune in then. Lee, thank you so much for an awesome presentation. Really appreciate your time. Audience, we really appreciate your time as well. Thank you so much for joining. We look forward to seeing you again next week for another Arm Tech Talk, and to joining us at Embedded World as we show that, Embedded World and AI really does run on Arm. Lee, again, thank you so much. Audience, we'll see you again next week. Take care.
See you.